So now that we have that silly example out of the way, let's see if we can't massively simplify the example to learn something from it. And from our perspective, if we want to do something with examples, we probably want to try to use matrices. So let's now forget the cat example, which is a complicated photo of a cat, and let's look at the easiest possible example. Let's say that the image that I want to study is a solid red rectangle, and this solid red rectangle is a vertical, or is vertically has size m pixels, and horizontally has size n pixels. Well, the first basic idea is that the data in this image can be represented by an m by n matrix. So this m by n pixel photo or image that's just all colored red can be represented with an m by n matrix, where each entry in the matrix is the data of a red pixel, which I will just represent with the letter lowercase r here. Well, one thing I'll point out is that we can compress the data in our image by factoring our matrix. Let's say for the moment that we want to look at a 2 by 3 pixel red rectangle. Well, one thing to notice is this 2 by 3 matrix factors as a 2 by 1 multiplied by a 1 by 3 matrix. Here, the 2 by 1 matrix we're studying has entries 1 and 1, and the 1 by 3 matrix has entries r, r, and r. Why is this useful? Well, if we think about the data necessary to communicate the information inside of our original image here, I like to call this the uncompressed image. And here it takes 2 times 3 pieces of information, which is 6 to communicate all of this information. So I need to know about 6 different positions inside of this original image if I want to represent my solid red rectangle. However, on the right-hand side of this equality, I like to think of this as the compressed image. Here, if we just count up the pieces of data we need to express this factorization, there are 2 entries in this first matrix. So this 2 by 1 matrix has 2 1s inside of it. So that's 2 pieces of data. And this 1 by 3 matrix has 3 entries inside of it, which is 3 pieces of data. Well, in total, 2 plus 3 equals 5. So by factoring our 2 by 3 matrix as the product of a 2 by 1 and a 1 by 3 matrix, we actually save ourselves 1 piece of information, and we don't lose any quality in this process. So by factoring, we losslessly compress our image, and we save 1 unit. Now, this might seem somewhat silly. After all, the difference between 5 and 6 is not that great. However, if we scale the example, we realize that this actually can be quite useful. So for instance, on a 4K UHD monitor, the resolution is 3840 pixels by 2160 pixels. So if I wanted to color a 4K Ultra HD monitor red, I could represent that information with a matrix that has 3,840 rows and 2,160 columns. So I can represent that data with our matrix, and I can apply the same idea behind the factorization we just presented. So I can factor my 3840 by 2160 large matrix, where every entry is tagged with the letter R, as a column matrix with 3,840 columns, multiplied by a column matrix with 3,840 rows, multiplied by a row matrix with 2,160 columns. And if we take a close look at the data requisite to communicate this information, if I just wanted to look at the original matrix representing the image, and I wanted to count all of the pieces of information inside of the image, I would multiply 3840 by 2160, and I would get a number that's roughly 8.2 or 8.3 million. So there are between 8.2 and 8.3 million pixels inside of this matrix. However, when we factor the matrix, the first matrix here has 3,840 entries, and the second matrix has 2,160 entries. When I add the pieces of information up, I get 6,000. And 6,000 is certainly far less than 8.2 or 8.3 million. So our compression is much smaller, and we haven't lost any quality by imposing this or by doing this compression. So this actually turns out to be a really good idea. Now keep in mind, I am not saying that this is the best possible idea. The best possible idea for a solid rectangle would just be to send the data of the color we're using, which is one piece of information, the number of rows, which is another piece of information, and the number of columns, which is another piece of information. So we really only need 3 pieces of information to communicate this solid red rectangle. But the problem is that by thinking that restrictively, we don't allow ourselves to think about more complicated examples. So here, there actually is content in this factorization. Our uncompressed image requires lots of data inside of this big matrix, but by factoring the matrix, we reduce the amount of information needed to define it without losing any pieces of information. So let's look at an example where maybe the image is more complicated. So what you're looking at right now is the Swedish flag drawn to scale. So if you go into Wikipedia, you'll find the dimensions for the Swedish flag. And the Swedish flag is basically this blue background with a yellow cross down the middle of it. And the dimensions here are as follows. So if we go along the vertical here, there's sort of like a blue stripe that takes up 4 times n part of the space. Then there's this yellow stripe which takes up 2 times n part of the space. And then there's another blue stripe taking up 4 times n in proportion. And then in terms of the columns, here in the first part, there's a 5n sort of blue stripe that's overlapped by our horizontal yellow stripe. Then there's a 2 times n wide yellow stripe vertical. And then there's a 9n region in the horizontal space here. So the idea is that we can take the data in this image and we can represent it with a matrix. So if we go to every pixel here and tag the pixel with a B for blue and tag a pixel Y for yellow, we can partition a large matrix with B's and Y's to represent the Swedish flag. What is the size of this image? Well, how many rows are there here? There are 4n plus 2n plus 4n, which altogether is 10n. And how many columns? There are 5n plus 2n plus 9n, which is 16n. And 10n multiplied by 16n is 160n squared. So there's 160n squared entries inside of this matrix. If we stare at this matrix for a moment, we realize that this matrix doesn't have a complicated rank. So if we stare at the matrix, we can maybe see the structure here. Even though this is a very large matrix, there really are only 2 types of rows. The rows up top and the rows on bottom are actually the same. We start with some blues, followed by some yellows, followed by a lot of blues. And then the same goes at the bottom here. We start with some blues, then some yellows, and then a lot of blues. And then in the middle, we just have rows of yellows. So we have one type of row on the top and the bottom, and then another type of row in the middle, which suggests that the rank of our matrix representing the Swedish flag should be equal to 2. So the Swedish flag can be thought of as a rank 2 matrix. So how can we apply our compression idea here? The situation is a little bit more complicated because the rank is larger than a solid red rectangle. A solid red rectangle is represented by a rank 1 matrix, whereas our Swedish flag here is represented by a rank 2 matrix. Well, here's the idea. We can account for the 2 types of rows and then compress those rows and then add the 2 compressions together. So here we're looking at a sum of 2 factorizations. Our first factorization is a column multiplied by a row. The row that we're multiplying by is exactly the row type that we find in the top and in the bottom rows of the Swedish flag. That is some blues followed by some yellows followed by a bunch of blues. And then we're multiplying by a column full of 1s and 0s that are telling us where to place this row and where to ignore the row. So we place the row in a bunch of places up top and then a bunch of places on bottom, and then we ignore this row right in the middle. In our second term here, we're accounting for the middle yellow stripe. So in the middle of the Swedish flag, we have a bunch of rows of Ys. So now we have our row of Ys, and then we're multiplying this by a column of zeros and ones, where the zeros tell us where to ignore that yellow stripe, and the 1 is telling us where to place the yellow stripe. So we place the yellow stripe in the middle, and then we ignore the yellow stripe on top and on bottom. So what we're doing is we're taking a 10n by 16n matrix, and we're representing it as the sum of two other matrices, and each of these two other matrices is the product of a 10n by 1 with a 1 by 16n matrix. Well, how does the compression work here? Well, to fit a 4K monitor, it turns out we can set n equal to 216, and then we can count the amount of data needed to fit the image on a monitor. Uncompressed, what are we doing? We're replacing n with 216 here, and then multiplying. So here we're doing 10 times 216 multiplied by 16 times 216, which is roughly 7.46 million pixels. What about the compressed data? Well, with the compressed data, what we're doing is we're adding all of the numbers of entries we're using in these factorizations. So in our first column matrix, we have 10 times n pieces of information, which is 10 times 216. Then in our first row matrix, we have 1 multiplied by 16n, which is 16 times 216 pieces of information. Then in our next column times row, we have another 10 times 216 pieces of information, plus another 16 times 216 pieces of information. And then when we add all of these numbers up, we get roughly 11.2 thousand, or 11,232 on the nose. So we're saving a lot of data here. 11,000, even though it seems like maybe it's somewhat of a large number, is much smaller than 7.5 million. So by factoring our large matrix in this way, we're saving lots of data, but we're not losing any quality because this is an equality of matrices. Another thing to point out is we could save even more space here at the price of quality. So if we were to drop one of these two terms, that would mean that we would lose information about the image, but we would save data.